Good morning. Today, I'd like to talk about a slight extension involving the arc length calculation that we've done previously. To get started with, I need to look at a certain geometric shape. I'm going to think of having a shape that looks like a right circular cone, except part of the front has been cut off. This is going to be characterized by three numbers: the larger radius, the smaller radius, and the length along the edge of the truncated cone, which I'll just call L, since pretty soon I won't be calling it a single letter anymore. I want to imagine taking an X-Acto knife and cutting this right down the side here, and then flattening it out. This circle, which had radius equal to big radius, will then become an arc of a circle with distance along this arc being 2 pi times the big radius, since that's the circumference of this larger circle. This will correspond to a distance of 2 pi times the small radius, and these are distance L. It's not difficult to prove that the area of such a thing is given by the following formula. The area is 2 pi times what I'll just loosely call a radius times the L number. The radius that I'm speaking of here is some number that's between the big radius and the small radius. If I wanted to be exact about it, it turns out that this is the average of the big and small radii. The problem that I want to look at is this. I've got the graph of some function starting at A, ending at B, and I'm going to revolve this around the x-axis, at least to start with. This generates some sort of three-dimensional shape, but this time I'm not interested in knowing the volume of that shape. I want to think about the lateral sides of it, which means the part that is generated by moving around in a circle, each one of the points on the graph. I am not including that part or that part. I'd like to know how much area is generated in this way. By now, surely it comes as no surprise that I'm going to split the range of x values up into many smaller pieces and look at what happens with one of these small pieces. If I make the pieces small enough, the curve looks more or less like a straight line, so when I revolve it around the x-axis, I end up with a shape of the type we were just looking at, with the horizontal distance delta x number I. I know the area that goes with this is 2 pi times a radius, we'll have to speak about the radius in a moment, times the amount of length along the edge here. But we know how to estimate amounts of length along edges, that's arc length. The amount of arc length along the edge is approximately 1 plus f prime ci squared, take the square root of that, multiply by delta x number I. To get the area that I'm interested in, though, I need to take that chunk of arc length and multiply it by 2 times pi times a radius. Whatever this c sub I is, I'm going to choose my x in my diagram here to equal that c sub I. My radius is going to be the y-coordinate on the graph at x equals ci. I have to emphasize, though, if it wasn't the x-axis that I was revolving around, figuring out the radius might be a little bit more tricky. The chunk of area that goes with this one subinterval, then, is going to approximately be 2 pi times the function value at ci, that is the radius in this case, times the square root of f prime at ci quantity squared times delta x number I, because that's how we figured out we would calculate arc length in this scenario. Surely it comes as no surprise to anyone by now what we're going to do. We're going to add up all of these contributions, take the limit as the norm of the partition, the biggest of the delta xi's, tends to 0, which turns it into an integral. Some people will want to memorize this formula and claim that it's universally valid, but we've seen in many other examples, if I'm rotating about something other than the x-axis, or in the other case, other than the y-axis, things get a little tricky. So I urge you not to memorize formulas. As an example, I'd like to revolve the graph of y equal x squared plus 1 about the x-axis. I'm going to look at the piece of the resulting shape that starts at x equal 2, ends at x equal 3. So this corresponds to x equal 2, that x equal 3. According to my recipe, I'm supposed to have 2 pi times the radius times the amount of arc length that goes with this given chunk. I'm not going to draw in as much detail now as I had in the past. I will have some chunk that's delta x number I wide. I'll select a c number I as the typical x value. The y coordinate is going to be the radius since I'm revolving this around the x-axis. The y coordinate when x is ci is ci squared plus 1. I have to multiply that by the amount of arc length that goes with chunk number I, but we've figured out how to do that as well. You figure out what dy dx is, square that, calculate the square root of 1 plus that quantity, and then multiply by delta x number I. Here, dy dx is going to be 2 times x, so when I square that, I'll get 4 times x squared, evaluated at x equals ci, of course. So this is 2 pi times the radius times the arc length. Then we would add up all such things, take the limit as all of the delta x's tend to 0. By now, hopefully, no one is very disturbed that I'm just going to write the integral down. The amount of area that we're interested in is equal to the value of this integral. As I may have mentioned previously, in our next upcoming major topic, we're going to look at making our collection of integration techniques much bigger. At the moment, we don't know how to do this integral in a nice closed-form antiderivative type scenario. We could get the calculator out and get a numerical estimate for the integral, or I could just delay that until we've talked more about integration methods. I believe I'll do that second thing. So on any kind of assignment, if I ask you about surface area, I'll be asking you to set the integral up. So this would be your answer in that case. As another example, I'm going to take the graph of y equal sine x, starting at x equals 0, ending at x equal pi over 2, which is the first positive value where sine takes on value 1. I'm going to take that graph and I'm going to revolve it around the horizontal line where y is equal to 2. This will demonstrate that you have to be careful about what you're calling the radius sometimes. I am not revolving about the x-axis. Y on the graph y equals sine x is not the radius. I am not doing that. I'm doing that instead. The radius is going to be the distance from the chunk that I'm looking at to the axis of rotation. So expanding my picture as we usually do, Here is the axis of rotation, the line y equal 2. In this case, the piece that I'm going to revolve is below that. If we keep straight our upper minus lower and rightmost versus leftmost, though, that doesn't bother us in the least. I need to know the radius, and I need to construct something that represents the arc length along this one chunk. The radius is going to be 2 minus the y-coordinate on the graph, where x is equal to ci. The radius will be 2 minus sine of ci, this y-coordinate, minus that y-coordinate. To do the arc length, I have to have 1 plus the square of dy dx, the derivative of that's cosine x, square root of 1 plus cosine squared at the representative x value times delta x is the amount of arc length that goes with chunk number I. Then we add up all of the 2 pi radius times arc length, take the limit, and obtain an integral. The area of the surface we're looking at is the integral from x equals 0 to x equal pi over 2 of 2 pi times 2 minus sine x times square root of 1 plus cosine squared of x with respect to x. As before, at the moment at least, we don't know how to do that integral in closed form. So again, in such a question, I would ask you to produce this integral. If it's not y as a function of x, but x as a function of y, and I'm not revolving around the x-axis or a line parallel to the x-axis, you can still do similar kinds of things. In this situation, I'm going to take the graph of the function x equals y squared plus 1, starting at y equals 0 and ending at y equals 3. I'm going to revolve that around the y-axis. I'd like to calculate the corresponding area. Just like before, all I need to do is to figure out the radius and the amount of arc length that goes with a given chunk. Since I'm revolving around the y-axis, I'll split the y range up into smaller pieces. When y is equal to the representative y value in chunk number I, the x-coordinate will be c number I squared plus 1. This is this distance. This is the radius of the piece of the graph that I'm going to get when I revolve around the y-axis. When y is a function of x, the chunk of arc length was the square root of 1 plus delta y over delta x squared times delta x. In this problem, the roles of the variables have been interchanged. I'm beginning to adopt the notation that I already know, generally speaking, how this is going to go, so I don't need to write quite as many details down. dx dy is 2 times y. If you square that, you get 4y squared. This quantity will be the square root of 1 plus 4y squared dy when all is said and done. If I wanted to be picky about it, I really should write that as the amount of lateral surface area that goes with this one chunk. But as usual, we're going to add up all of these things and take the limit as all of the delta y's in this case go to 0. And as with many other cases, we end up with a perfectly nice integral. There's nothing at all wrong with any of these functions. We simply don't know how to do an antiderivative in order to evaluate the function in that way. Later on, during the vast and horrible discussion of integration techniques, we'll make a substitution. We're going to let 2 times y equal tangent of some other variable. That'll make the square root work out nicely. It'll transform the rest of it into a bit of a mess, but we will develop recipes to handle that sort of situation. I believe this is all I'm going to say about lateral surface area. I hope everybody's having a good day, and I'll talk to you again soon.